a straight line. So quickly I have taken an example next to this slide. It is one of the example which we saw in in, uh, in one of our previous classes, the previous class itself, K5. But however, there is no edge between V1 to V4. It is not a complete graph of 5 vertices. There is one edge missing. So if we count, there are 5 vertices and 9 edges. So this is a planar graph and it is a simple graph. Oh, I didn't notice that my screen got stopped sharing. Hope now it is visible to all. Yeah, even messages went off. Probably I reconnected. I'm still in the lab. There are some problems in the given cabin. So hopefully today there won't be any technical glitches. If there are, then probably I will connect in no time. Just a heads up. Be patient and excuse me upfront. So this theorem, what it says is any simple planar graph which can be embedded on a plane such that every edge can be drawn as a straight line segment. So I have taken a quick example here. Graph figure D. I name it as a D here. So this is not a K5 graph. One of the graph which we saw under Kurotowski's observation, K5 and K3.3. This is one of the step where we try to prove that the given K5 graph is non-planar. In that one of the steps, this is last but one step graph which has 5 vertices and 9 edges. K5 graph has 5 vertices and 10 edges. Means every pair of vertices there is a vertex, but however in this case there is no edge between V1 to V4. And this is a planar graph which can be drawn on plane, embedded on plane. So can we make this through a straight line is the question. That's the theorem. Any quick answers here? So the proof is, as an illustration, the graph, the figure D, can be redrawn using straight line segments. But definitely figure E is the result. Yes, it can be redrawn. Just for visualization purpose, if I push V1 and V3 to closer to each other, V2, V1, V3, V5, V4, if I make that as a rectangle, sorry, why did I say rectangle? It's my mistake. It is triangle. Means V2, V1, V5 comes in straight line. V2, V3, V4 comes in a straight line. V5, V4 being at the same position. V1 and V3 comes closer and V2 at the top. So it becomes a kind of triangle, but however, there are 5 vertices. Then V2 to V5 and V2 to V4 can be drawn in a straight line. That is one way of representing it. Again, I will state the theorem. Any simple planar graph can be embedded in a plane such that every edge is drawn as a straight line segment. But however, I have shown in another way just now, which I try to express, try to visualize, that moving V1 and V3 vertices closer to each other will make everything straight line. This is a straight line representation of graph figure D, or probably graph in figure D. So if we closely look, the number of vertices are same, 5, and the number of edges 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we can see 3 triangles in that. Base being the same, right? Base being the same. So every 3 triangles constitute to 3 edges. Since base being the same, it becomes 7 edges, right? 3 plus 2 plus 2. That's 7 edges, and in between these 2 edges, it is 9 edges. So this is a different representation of a graph D or figure D. through straight line. This is one of the theorem under this topic. Any doubts? Yes, we can represent in another way also, but it will become the another representation of planar graph. Shall I move to the next slide? Okay. And a very important topic, I made this simple green color because in this theorem it is necessary for a graph to be simple. Why? Because a self loop or one of two parallel edges cannot be drawn by a straight line segment. Self loop definitely, even parallel edge between two pair of vertices, it will, if I do a straight line, it will coincide, right? It will overlap, it will become a single edge. To represent two different edges for the same particular pair of vertices, it has to be non-straight, bit curvy. So in that sense, the theorem itself, any simple planar graph, simple is the keyword, planar is the keyword, embedded in a plane. These are all keywords which makes a graph with all their edges with a straight line. Going to the next, a small concept under different representations of a graph, region. Now, region has, we already have a fair idea what is region about. It is a space surrounded by some boundaries, right? Some boundaries, this is the region. Or boundary, it can be through edges or set of vertices. We'll see what actually it is. A plane representation of a graph divides the plane into regions, also called windows, faces, or meshes. We'll stick to regions. In few of the occasions, I will explicitly tell face, or probably not more than, I won't make use of windows or meshes going forward. Region, to be precise, sometimes face. So I have shown a figure here. Before going to that figure, we'll quickly see what actually the region is. The region is characterized by a set of edges or set of vertices forming its boundary. So we now understand what is region is. With respect to this graph, there are, how many regions are there? I already named it. Highest number is 6, right? 6 regions are there. I have already shaded also that part, set of edges into different, not different, right? Almost same side shading. This being the one region, 2, 3, 4, consisting of everything outside, 5 and 6. There are 6 regions. Now quickly, can someone tell how many exact edges are required to make a region, to have a region? Can someone? How many edges are required to have a region? Yeah, one self loop. One is good enough. One is good enough. One self loop. I'm not no more talking about simple graph now. It is in general. Region is a concept which is applicable to graph. Till now, when we discuss about graph, trees, and previous concepts, when we say graph, we had the mindset of vertices set, right? Edges set. So along with vertices and edges, there is something called region also. Now we are introducing region concept. We are moving a level up from a concrete graph to planar graph. When plane comes into picture, region comes into picture. If I draw this graph in an Euclidean 3D space, then it is highly difficult to imagine the region, right? The region concept closely attached to planar graph, which can be drawn on a plane or embedded in a plane. Okay. Note that the region is not defined in a non-planar graph. See, as simple as that. That was the next point. The region is not at all associated to non-planar graph, or even in planar graph, which never been embedded in a plane. There's a graph, planar graph, but never been embedded in a plane. Such graphs also, there is no concept of regions until unless the graph has been put on to a particular plane, a particular representation. Then only regions are identified or labeled. So, for example, the geometric graph figure B, this is the figure B, doesn't have regions. Thus, the region is a property of a specific plane representation of a graph and not of an abstract graph. If I give this, graph details abstract way, definitely many of the students right now it's not a planar graph because the already the embeddings crossing over. The edge E and F are crossing each other. Definitely, even though the other representation of this abstract graph can be made it as a planar, but this graph is not a planar. So if I give this abstraction, there's a high probability that students, you all might make a planar graph and regions, the embeddings on a plane will ultimately give a origin to the concept called regions. So till now, any questions? Okay. The silence effect I will take accordingly the way I want to. So I consider there are no questions. Okay. Now moving to infinite region. So we already quickly saw in our previous 4. I already told this 4 region is an infinite region. 1 is bounded to only this. 2 is bounded to this triangle. 3 region is bounded to this triangle. 5 is bounded to this triangle, and 6 is bounded to the circle. 4 rest of the region is part of 4. That region is not finite region. There is a concept called infinite region. We'll quickly see. The portion of the plane lying outside a graph embedded in a plane, such as region 4 in figure A, is infinite in its extent. Such a region is called infinite unbounded outer or exterior region for that particular plane representation. For that particular plane representation is the main important thing. Okay, it's always one particular exterior region for the given particular plane representation. It is tightly bound. If the plane representation is something else, the region becomes, the the geometric representation of that particular region or the surroundings of that region will change. So it is all about particular plane representation. Like other regions, we'll quickly see. That's why this example I have taken for to understand this second line. Especially that particular plane representation. If we closely see, D and E are isomorphic graph. Can anyone tell me whether the graph D and E are isomorphic graph? Ramesh Kumar says yes. Okay. And others? Closely look into all the vertices, their degrees, and the labelings. Here I have already given the labeling, so you just have to do 1:1 mapping. Whether the semantics are mapping. Yes, it is. It is an isomorphic graph. It is an isomorphic graph. Correct. Yeah, I started getting the messages now. Yeah. So both are isomorphic graph. Means two different representation. Especially I will put it in this way, but two different plane representation represented on a plane, right? So two different representation of graph. If we look closely, the the vertex v1, v3, and v5. In the upper graph, v1 vertex, v3 vertex, and v5 vertex. The region which is inside this v1, v3, v5 is a region. It's not an infinite region. It is just a region. Means limited region. Similar vertices, if you look for the graph E, v1, v3, v5, becomes the almost outside of all the embeddings, and the region it belongs is exterior region or infinite region. So the region which is in finite here becomes infinite in the other, even though the both are planar graph, right? We can embed both are isomorphic graph. What's the difference? Why the regions have changed from infinite to infinite is mainly because of different representation or a particular plane representation. Able to understand, students, why this different representation of planar graphs is coming into picture? Till unit 3 we just went with the idea of graph, then suddenly abstract graph came into picture. Just with the abstract graph, these concepts have never been existed, right? Because the way we draw it entirely changes. As there is a geometric representation of graph for every abstract graph, and that particularly can be drawn on a plane, so planar graph came into picture, and that is not good enough. We have to mention that explicitly, that the plane representation, this is one of the plane representation. The same graph can be made, the same graph can be made, as I starting of this class told, v1 and v3 can be narrowed down or made it closer to each other. In that, again, it would have become the planar graph, simple planar graph with straight lines, and it is again a different representation in a way because the edges are not curly, or the edges are not in the modified, the edges will be straight line. So that's why I said particular plane representation is a key thing here. Now, moving to a concept called embedding on a sphere. Right now, we have all embedded the graphs on plane, and because of that, slight representation change becomes finite, infinite. That's a mess, confusion there. So there is a concept called embedding on a sphere. To eliminate the distinction between finite and infinite regions, a planar graph is often embedded in the surface of a sphere. What that means is, we go to quickly to this image. This outside, kind of a rhombus, or probably what this shape is called, not definitely a rectangle, not rhombus also, it is, by the way, this edge and this edge is parallel. Parallelogram, correct. This edge and correct, parallelogram. I was unable to recollect that. Yeah. So this edge and this edge is parallel. It's just an idea of representing. It's a plane. It's a side way of seeing. It is kept on a floor and it is kind of plane. And on that, the sphere has been put. Okay. So embedding on a sphere, before representing any graph on a plane, first the sphere will be kept on a plane and then the graph will be embedded on a sphere. That's the idea here. Just to more understand with respect to reference about finite and infinite things. It is accomplished by a stereographic projection of a sphere on a plane. So yeah, this figure is about stereographic projection. What projection we did? We did a projection of a sphere on a plane. Put the sphere on the plane and call that point of contact is South Pole. Now this has been kept on a plane and that the point of contact is called SP South Pole, and the perpendicular to that the other point is called North Pole. Okay, NP. Okay, at the point SP, draw a straight line perpendicular to the plane and let the point where the line intersect the surface of the sphere be called NP. Okay, as shown in the figure. Now, corresponding to any point P on a plane. So there's a point P. Or directly connected to north plane. Now corresponding to any point P on a plane, there exists a unique point P dash on a sphere and vice versa, where P dash is the point at which the straight line from point P to NP intersects the surface of the sphere. With the straight line from NP to P, there is a point which differentiate plane and sphere, right? That point is P dash. Similarly, the vice versa thing is, if the point is in sphere and the P dash is in the plane, again, that to have just a reference such a way that why we are keeping the sphere, the main concept is sphere can be rotated, right, in a Euclidean 3 distance. Right now, whatever the representation we are making on a plane, it will become a rigid. So just imagine that if we put some rangoli type of thing on a floor, it becomes rigid. Imagine if you do a rangoli on a glue balloon, right, and you can rotate it and the representation, the diagram is same, the graph is same, but when you rotate it, that illusion visualization will change. To have that reference, the P dash has been mentioned. So thus there is a one-to-one correspondence between the points of the sphere and the finite point on the plane. So definitely there is one-to-one correspondence. We can have a reference, any graph which is embedded on sphere, okay, and immediately we can make some points on plane and can have a one-to-one mapping such a way that, okay, the vertex V1 is at here and very close to P, and the dash is vertex V1 dash, which is just moving from sphere to plane, V1 dash. And then when we rotate that to make the finite and infinite things won't mess up, like just in the previous example it did when we changed that representation by moving here and there, infinite thing becomes an infinite region. To have that a reference, usually the graphs are represented on a sphere. Now we are still at region, okay? Still we are trying to understand more about regions. So suddenly Euler comes into picture. Euler formula. Since a planar graph may have different plane representation, very important point here, since a planar graph may have different plane representation, we may ask if the number of regions resulting from each embedding is the same. Now understand the question. Euler made a very good point here. Even I did mention that a given abstract graph which can be embedded on a plane, and it can be with different representation, and in all the different representation the number of regions will remains the same or not. It is okay to represent however the way we want, but as we have number of edges are same, number of vertices are same, is that number of regions are also same? That's the question. Till now, before going into these concepts, region was not at all being introduced. So when we went with isomorphic graph with two graphs, we check those vertices are same, edges are same, degrees are same, and stuff like that, right? To cross check. Or probably spanning tree. If we take for a given graph, there are multiple spanning trees. So each representation is different, but the number of vertices and edges are same, n minus 1 and n, right? Similarly, for a given planar graph, each planar graph can be represented in a different uh, planes, which can be different in a multiple ways on a plane. Whether the number of resulting regions for each of the graphs is same or not. So the answer is yes. The answer is yes. I already highlighted that, and we'll quickly come to the theorem. A connected, again a keyword connected planar graph with n vertices and e edges has e minus n plus 2 regions. That is, I call this f. F is region. F can be a face also. R into f. F equal to e minus n plus 2. What is the proof? This is a bit of tricky way. Before going to that, imagine there is no graph, no vertices, nothing. Okay. Now I will add a just one self loop. How many regions will become? Can someone tell? Think. I just added a one self loop. I didn't say simple graph. That is just a connected planar graph. Right now there is no graph at all. However, now I have added on plane just one simple self loop. Kamesh says 1. So 2. One finite and one infinite. Correct. Exactly. So there are two regions. One is inside, that is finite region. Don't have to explicitly mention finite. Infinite requires. There is a one region inside and the exterior is an uninfinite. Exactly two regions. So if we put E, how many edge? One edge, self loop. How many vertex? Only one vertex. 1 minus 1 is 0. Left out what? 2. So number of regions are 2. You can quickly tell with this formula, given number of vertices and number of edges, we can tell that how many regions are there. Can quickly someone apply for this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. 6 number of vertices, edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 minus 11 minus 5. No, not 5. 7. 1, 2, 3, 4, 5, 6, 7. 11 minus 7 gives to 4. 4 plus 2, it is 6. So it still holds good, even though there is just a simple edge outside, In fact, two edge, not two edge. There are three edges. It's never contributing to any region. That is from here to here, here to here, here to here. By adding an edge, definitely vertex also will be added, right? By removing an vertex, definitely edge also will be removed. It is that E minus N will be balanced always. What I meant was, we'll quickly see this. I mean, probably we'll get to understand the more. Okay. So it will suffice to prove that the theorem of a simple graph, yeah, it should be connected. Okay. Theorem for a simple. Considering that it is a simple graph, because adding a self loop or a parallel edge simply adds one region to the graph. In my example, I have taken a fresh graph, then I have added a self loop. Consider there is already a graph, and when we add a self loop, it will just add one extra region that is inside that self loop, because exteriors are already there in that graph, right? So this, this edge 6, if I make that inside here, the only thing the extra region is coming is that the inside that self loop. Outside it's already there. You put this self loop anywhere to any vertex, it just adds one. So adding one edge will just adds one extra region by value just one. We can also disregard or remove all edges that do not form boundaries of any region. Like if we remove these three edges which are not contributing to any region, by removing these three edges, if I remove, how many vertices will be removed? Ultimately three. If I remove three edges, three vertices are left and they are discrete keyword connected planar graph. So if I'm removing it, definitely I will remove those edges also. Three edges are removed. Ultimately, three vertices have also been removed. So still the number of regions are unaltered. That is, E minus N is unaltered. Right? This very classic, important formula to calculate the number of regions only for connected planar graph. Okay? Connected planar graph. It can be a gate question also, can come here and there related to this. Any questions, students? Okay, we'll move to a quick corollary. What we saw is exactly opposite. What it corollary says is, in any simple, now we are coming to from just a planar graph to simple. In any simple connected planar graph with F regions, N vertices and E edges, where E is greater than 2, the following inequalities must hold. If they are simple connected planar graph, then definitely these inequalities, that is this inequality and this. Why it is inequality? It is greater than or equal to or less than or equal to. That's why the inequality. These equations holds good always. Must hold good. That's the corollary. Closely observe that corollary in any simple connected planar graph with F regions, N vertices, E edges, where number of edges should be greater than 2. Means there should be 3 edges. These inequalities must hold. Okay, the one is E should be greater than or equal to 3 by 2 of number of regions, or E is less than or equal to 3n minus 6. We'll try to see what are those. Proof: since each region is bounded by at least 3 edges. Why I went for 3 edges here? Why not just one edge? I will repeat that. Since each region is bounded by at least 3 edges. Why I am doing this statement? Can someone tell? 3 edges. But during the starting of this, the previous theorem, I just started with a single self loop. How many regions will be done? Answer were 2. One is inside, the one is the exterior. Now I say for each region is bounded by at least 3 edges. I'm contradicting here, right? Anyone has an answer to that? A triangle, triangle, 3 edges. definitely there is an edge. 3 is the minimum. Kamesh says 3 is the minimum edges required to form a closed polygon. Yeah, but what about self loop? That doesn't make any self region. Exactly. Joyce is there the answer. See, corollary, you should. I mentioned that in any simple corollary, by planar graph. Okay. When we word use simple, definitely, many of the things are filtered out there. Exactly. Simple graph avoid self loops. So, since each region is bounded by at least 3 edges and each edge belongs to exactly 2 regions, so that each edge will participate in the interior and the exterior, or probably the other side, right? So that can be written 2 into E greater than or equal to 3F. Any difficulties in understanding this? Will quickly help you out. Take a simple graph of 3 vertices. 3 edges are there. Okay. So if E is equal to, let me put 3 there, 2 into 3 is always greater than or equal to 3 into F. 2 regions are there. It will become 6 there. That's why the equal coming into picture. So if I push that E to denominator side, it becomes one of the inequalities which always holds good. E is greater than or equal to 3 by 2 F. This inequality is only applicable to simple graph. And now we already know F equal to E minus n plus 2. If we substitute F with respect, if we try to express this part, the first part in terms of E and n, we'll get the second part. You get that second part. These inequalities is often useful in finding out if the graph is non-planar. Means if there is a graph, simple graph, we want to check whether it is a planar or non-planar. If we remember these inequalities, if we just try it out, then we can tell it's a planar or non-planar. Is that so? We'll try to see it in the next example. So I have taken the K5 graph. It's a non-planar graph. We know that because we try to prove it through one by one. First, we did we took one. So like that, we did try and we saw that K5 is a non-planar. We can validate that. Now n 5 equal to 10. I don't want to. So yes, regions I can calculate it, but I just want to express in terms of E and N. So I will go with this equation. This equation. E is less than or equal to 3n minus 6. So I put that E is less than equal to 3n minus 6. 10 is less than 3 into 5, where 5 is number of vertices. And the equation comes is 10 is less than or equal to 9, never. Thus the graph violates inequality, hence it is not planar. What we just saw, first we proved a theorem that number of regions for any representation for a given graph, planar graph, connected planar graph, we just figured out how to calculate the regions. Now with that knowledge, we went with a corollary that for simple graph, two inequalities, simple connected planar graph, these two inequalities should hold good. Okay, work very well. the equation, I just got number of edges and vertices, and it violating it. Hence, the graph is not planar. I will quickly move to the next. What is this graph? Anyone tell? We saw this in last class. K33, exactly, K33 graph. So how many, we did some inference also, of vertices are 6, minimum number of edges 9, right? If I remove one edge, it's a planar, right? Such things we saw in the previous class. So we'll quickly apply that same thing. N equal to 6 equal to 9 is less than 3n minus 6, same equation. 9 is less than 3 into 6 minus 6. It's 16 minus 6, 12. This holds good, but still it is non-planar. Right? What is the problem now? Inequality is only a necessary but not a sufficient condition to say that given graph is non-planar. Means if that inequality doesn't hold good, then blindly we can say non-planar. If the inequality holds good, we can't blindly say it is a planar. We still have to figure it out. In this case, the inequality is holding good. We can't just label that as a planar because it is still a non-planar. Get that? It's necessary condition, but not the sufficient condition to label non-planar correctly all the time. If doesn't hold good, then directly we can say that. If it is not holding good, so if the inequality is not holding good, then directly we can say that the given graph is non-planar. If it holds good, no, that is not a good enough condition. Any question with respect to till now? What about different? Yeah, I'll go to the next slide. To be remembered, in a disconnected graph, suddenly I am coming to a concept called disconnected graph. Okay. Connected graph. In a disconnected graph, the embedding each component definitely yeah, am I audible? The screen is visible. Hello. See that because voice is audible. Okay. Okay. Let me share my window again. How about now? Screen and my voice both are okay? Okay, thank you. So Yeah, thanks, Aaron. Thanks, Joyce. Point what have made planar. Then the whole disconnected graph is also a planar. We started the concept of planar in a connected way, but also disconnected graph can be also a planar only if all its components are planar. That is one first point with respect to connect. Why I have made that in under connectivity is because of disconnection, plane representation and their connectivity. If it is not connected completely, then it is disconnected, and their each plane representation, that is planar graph. Similarly, in a separable graph, what's separable graph? One connected, one vertex. If I remove that, the whole graph will become disconnected. Similarly, in a separable graph, the embedding of each block. So I can still imagine, probably you guys are also, the one graph which having a vertex v at the center. If I remove the vertex v, the whole graph will be disconnected, right? So the left hand side part is a one block, the right hand side is the other block. Now with respect to that, I could have put that in graph. My mistake, I didn't, but still we'll go with that. In a separable graph, the embedding of each block. Now definitely there can be multiple blocks, but considering that the only example, left and right, both the blocks, if we consider that independently, and separable graph becomes a planar if and only if all the blocks are also planar. Similarly, the way we did for component in a disconnected graph, blocks are also, if they are planar, then the whole separable graph becomes planar. So there is a bit clear understanding with respect to planar graph, not just in a connected graph, even for disconnect with respect to embedding or planarity with respect to disconnected or unconnected. However, the question still arises when it comes to non-separable graph. Okay, yeah, I will. Am I audible now? Hello, am I audible now? Yeah, it's thank you, Jagan. Thank you, Joyce. See, already it's been 2:22. I will continue in the tomorrow's class regarding the discussion with respect to disconnected and non-separable graph. Hope there are no questions. If any questions, well, I will take them in the next class. Thanks everyone for joining. Hope CR has taken the attendance.